fall down 7 times, stand up 8. And this, of course, is about resilience. You know, you're going to have challenges in life. And as Rocky Balboa put it, life ain't about how hard you hit. It's about how hard you get hit and you keep getting back up. And so don't let one bad exam stop you. Your grade isn't determined by one exam. Now, it is an indicator. I won't deny that. But that doesn't mean it's a guarantee. And so you can change your outcome. So stand back up and keep going. All right, what's our goals for today? Well, new section. You know, our class has 3 components. And we finished our first component, which was applications of integration. In other words, setting up integrals. We're moving into component 2, which is techniques of integration. And perhaps that's what happened on the last exam. People are like, I could have done better if they only let us do more integrals. Well, we'll let you do that on the next exam. Lots and lots of integration is coming. Now you might say, I'm feeling nostalgic. Do I still get to set up any integrals? Yes. There'll be a little bit of that. Not too much, but a little bit. And so as we start our techniques of integration, we are going to learn about integration by parts. So this block on your formula sheet is about integration. And there's this one little piece here. Essentially, all of this was learned last semester, but this is new. And that's integration by parts. And now you'll say, okay, where is the other stuff about integration? Well, we'll get to that. We'll get to that. All right. Well, what do we know? We go back to last semester. We said, well, we learned a couple of integrals, and so we have a list of things that we should know by heart, but you know, just in case we have a place to reference them. And I will say, when you take Calc 1, of the basic integrals, we usually talk about 8 of them. These 2 we don't necessarily hit very much, but they are still useful to know. The integral of tangent and the integral of secant. And that way you essentially have your collection of your trig functions. Now, I tend to avoid cosecant and cotangent, but basically the moral of the story is if you see a co in front of something, it just means you add a minus sign. You say, okay, so those are our basic functions we can integrate. What are some useful tools? And all our useful tools that we have so far come from rules for derivatives. So one thing we have is that derivatives are linear. In other words, if I'm adding 2 functions, I want to take the derivative, I can take their derivatives separately. Still true for integrals. If I'm integrating 2 functions and they're being added, I can break up over addition. Now, when I say break up over addition, there's the good plus signs and there's the bad plus signs. The good plus signs are the ones where you can actually decompose and break apart. Bad plus signs are things, for example, in the denominator. We'll talk about those next week. So, okay, so linearity for differentiation, linearity for integration. Then we have the chain rule. Beautiful rule, great rule. It's a really important rule because most functions are sort of pieced together and involve composition, functions inside of functions. And we can take that chain rule for derivatives and we turn it into the substitution rule for integration. We say, great, if I have integral of f of g of x, g prime of x, dx, I can make a substitution, give it a new name, u is g of x, and then I can turn it into a function f of u, du. And of course, this just means how do you find the right substitution? And that's not trivial. There's lots of subtle things that you look for. Of course, oftentimes you say, look for something on the inside, or you say, look for something where you have a nice derivative floating around on the outside. And those are your 2 clues for substitution. All right, so this came from our chain rule. Now, the last thing, and I wrote down the formula today, we're going to derive the formula, is integration by parts. And that comes from the product rule. So the product rule says, suppose I want to take a derivative of two functions. Then I can say, well, every function gets its term. Derivative of the first times the second, plus the first times the derivative of the second. And if you start with that and say, well, what does that mean in terms of integrals? You end up with what's known as integration by parts. All right, and we will get into details there. Now you might say, that's amazing. This is a good start. Where are we going from here? How many new functions are we going to add to our list of basic integrals? And the answer is, we're not adding any new functions. You might say, oh, okay, what techniques are we going to be adding about integration? That's it. So you might say, well, this is a very short section because we've already learned all this stuff. Well, we're going to learn to get better at it. And so what is our goal when we talk about techniques of integration? So as I've said, it's not about learning new functions. It's about using the tools that we have. The majority of work that goes into solving an integral problem doesn't happen at the stage where you take an antiderivative. That's oftentimes people think, okay, integration is about antiderivatives. And it's true, but it's getting to the point where you can take antiderivatives. That's where you work. The majority of the work happens before any antiderivatives occur. So you have to figure out, how can I get there? Because we have a very short list. We have 10 things we can take the antiderivative of, and that's basically it. Say, okay, so how do we get there? Well, we use various things. So we can use algebra. And we've used algebra before. We've done things like expand terms. And so one of the things we're going to talk about is partial fractions. And that's an algebra technique that you learned about. And when you learned it, you were probably wondering, when will we ever use it? And the answer is soon. In this class, next week, it's coming. We're going to learn about trigonometry. Now, we already see that there's a bunch of trig functions that we know how to take antiderivatives of. So we're like, okay, so what's left for us to do? Well, trigonometry is wonderful because there's a lot of identities. It's also annoying because there's a lot of identities. And what that means is there's a lot of ways to rewrite expressions. So we have to figure out, how can we use the identities that we have to rewrite things so that we can actually solve it? Now, it involves identities. I will say one of the things that we'll learn quickly is that algebra and trigonometry, we can sometimes jump from one to the other. We might have a trigonometry problem, and we'll cast it into an algebra problem by a substitution. But we can also have an algebra problem, and we can turn it into a trigonometry problem by substitution. And that's called trig substitution. Another idea which we'll talk about in the next few weeks. Now, of course, we have integration by parts, which is today. Two more topics which we'll talk about: improper integrals. And by improper, we just mean integrals which involve infinity in some way, shape, or form. How do we deal with infinity? Well, carefully. Weird things can happen. And finally, we're going to say, look, there are some things we just can't integrate. Now, in real life, this happens frequently because we have data. And we say, look, I don't have a function, but I have lots of data, and I want to understand the totals and how that works. And so we do what's called numerical integration, which says, okay, even if you don't have the function, but you have data, you can say, I can estimate what's the total. Now, it's not just for places where we don't have a function. Sometimes we have a function, and it's hopeless. It turns out integration is hard. There are functions that we know cannot be integrated where the answer is using functions that we already have. We'd have to make up new functions to write them. Now, yes, it's true that there are functions, because it's one of the things that we learned from fundamental theorem of calculus. If you have a continuous function, it definitely has an antiderivative. But it doesn't mean it has a nice antiderivative. And so we have to have ways to say, well, look, maybe we don't need to have the exact function. Maybe we only need an approximation. Maybe 4 digits after the decimal, and that'll be good enough. So that's another topic we'll talk about. And so how do you approach a problem? Well, roughly speaking, I quickly run through and say, hey, is this one of the basic functions I already know? If I have that, I'm good to go, antiderivative. Is there some algebra or trig I can apply? If there is, I do that, and then I restart. And then maybe I say, well, I haven't seen anything, and I say, well, is there a substitution? Substitution should be one of your first go-to things. It's an incredibly useful tool. And if I find a substitution, I can restart, and I start going through it again. Can I do it by parts? Now you might say, wait, why are you teaching us by parts, but you're putting it so far down the list? By parts should not be your first thing to try, unless you're very confident it works. It's sort of a Hail Mary. Maybe by parts will help. And if you can't do anything, maybe it's a numerical problem. Of course, on exams and quizzes, you'll know it's numerical. And there's a piece of advice. When you're looking at an integral problem, I like to think about it as saying, I'm trying to simplify. I have an integral I've been asked to carry out. So my goal is I have to get it simple enough that I can find an antiderivative. So I look at it and say, what can I do to simplify? And then as soon as I've simplified, then I say, aha, good. Am I ready to go, or do I need to keep simplifying? And so don't think of it as you always have to do things in one big step. Think of it as there's lots of intermediate steps. And just say, my goal is to simplify, simplify, simplify. All right. So that's the next few weeks. This is what we have to look forward to. And it's a very short section of the course. So the next exam is coming up in, well, it would be 4 weeks, but there's this break. So I think it happens right after spring break. Now, there's good things and bad things about that. The bad thing is, somehow, people forget a lot during spring break. But we'll talk about that as we get closer. All right. Any questions on where we're going in the next few weeks? Good. Well, then let's talk about where we're going today. Our sort of last tool, our last basic idea, integration by parts. I already mentioned it came from the product rule for derivatives. So we say, okay, every good rule from integration came from a rule from derivatives. And so we start by writing down the rule. So we have the derivative, derivative of the first times the second plus the first times the derivative of the second. And now you take the integral of both sides. Well, if I integrate the derivative, I get back the original function. And why is that true? And is it true? Well, technically it's not true, but let's ignore that fact for a second. But why is it true that if I take a derivative and then I integrate, I get back to where I started? This is something you should know. It's a very fundamental part of the course. Fundamental theorem of calculus. That basically says derivatives and integrals undo each other. Now, why am I slightly lying to you? When you take a derivative and then you integrate, do you get back the function? And why not? What's different? The plus c. Yeah, you're off by a constant. But of course, there's constants floating around over on these integrals, so we sort of hide it under the rug. Okay, so we essentially integrate both sides, and then you move stuff around. You say, all right, well, let's move, what terms did we move around? Here we did. We moved the f prime of x, g of x dx, subtracted it to the other side, and then we just sort of changed the order here. Now, the way it's usually written is in this form: u dv is uv minus the integral of v du. And what that means is we think of u as one of our two functions. So u corresponds to the f of x. Du would be f prime of x dx. V is the other function, g of x. So we see g of x, and dv is g prime of x dx. So the integral of u dv is uv minus the integral of v du. So that's integration by parts. And it works with both definite and indefinite integration. All right, that's the idea. Okay, so we have some notes here. Why do you call it by parts? Well, if you think about what's happening, is we're trying to integrate, but we're not going to integrate the whole thing. We sort of integrate the g prime, and so we're just integrating a part of it. And so ultimately what's happening is we're turning one integral problem into another integral problem. Now, that doesn't seem very helpful when you first hear it, but what's going to come from that? Well, what can happen is that the first integral problem, it may not be clear what to try, but in our new integral problem, it's a simpler integral. So you have a better chance. So again, the goal is simplify something. And if it's getting simpler, good. If it's getting more complicated, mistakes were made. So be careful. And another note, Mari said this, don't forget to check for other options. Sometimes we get our shiny new toy and we're like so excited. Integration by parts. I'm going to just throw that at everything. And you say, no. Apply it to the right things in the right situation. Sometimes there's better techniques. And substitution, if substitution works, it's always the better option. All right. Lots of notes, but don't worry. We're about to get into the meat here. Do some examples. Okay. So some general strategies. Check for an alternate approach. That means just don't forget to look for a substitution. You might need to use this in combination with other ideas. We'll explain that in a second. Sometimes, well, okay, I'll just say it now. Sometimes we think of techniques of integration as being in compartmentalized boxes. We say, okay, this problem will be an integration by parts problem, and that's the only thing we see. And we put our blinders on. Or we might say this problem is only a substitution problem. And again, that's all we see. But there are problems which can use ideas from both. We can blend ideas together. So don't get into the sort of tunnel vision that says, okay, I can only use this tool. You can use multiple tools. They'll happen at different stages. You should try to avoid doing multiple tools at the same time. But be mindful that you may have to use different ideas. Now, the last thing, and then we'll get into problems here. How do you find which things should be u and which things should be dv? And there's some various acronyms that people have come up with. I don't do that. I say, what makes a good candidate for u? Well, what's happening to you? If you go back to the formula, you say, the u is going to be the thing you take a derivative of. You say, okay, well, what should be the part that you take a derivative of? Something that you can't integrate. So if you see something that say, oh, that's hopeless to integrate, that's probably your u. And another thing is powers of x very often is your u because it can go to 0 with enough derivatives. How about your dv? What should you be looking for? Well, you need things which are easy to integrate. And so things like e to the x, or sine x, or cosine x, those are fairly stable. And keep in mind, 1 is an option. Now, the last piece of advice, when in doubt, try something. Try something. If it doesn't work, try something else. It's okay to try something and say, well, that didn't work. You've learned something. That's valuable. And you say, all right, now I go forward and I learned something else. All right, so here we go. Finally, we're ready. We have a couple of integral problems to do. Find 3 integrals, so we won't do them all at the same time. Let's start with the integral of x e to the x. Now, is this one of our basic functions? No. Is there a good substitution here? No. Parts. Can we do it by parts? Well, hopefully. I mean, that's our goal. What should we be setting our u? What should we be setting as dv? Okay, so I think people are saying u and dv. Essentially, we have 2 functions. So oftentimes there's the mindset if I have 2 functions multiplying, one of them is the u, one of them is the dv. It can be a little bit subtle, but we'll save that for later examples. I say, okay, would you rather take the derivative of x or take the integral of x? If you integrated x, what would you have at the next step? You'd have like an x squared. And the question is, what's an easier integral? The integral you have now, which has x e to the x, or the integral x squared e to the x? Well, you don't want to do x squared. X is simpler. So that's sort of a clue, like, yes, we should definitely take our derivative. Okay, so if u is x, what is du? Okay, it's 1, or I would write 1 dx. And what is v? E to the x. So you have to do a small antiderivative, small integral problem. All right, so we have the integral of x e to the x is equal to, well, we have our u, v, so x e to the x. And then we're going to subtract the integral of v e to the x du. All right, so there we have after one stage. And now you'll say, okay, well, x e to the x, didn't know how to do that right away, but e to the x, can we integrate that? Yes. What's the integral of e to the x? E to the x. And of course, don't forget to add plus c. And there we go. Okay, so that's not so bad. Well, let's do another problem. Integral x e to the x squared dx. All right? What can we do? U sub, what would you like to U sub? I'm not saying it's wrong, I'm just asking. What should we do for a U substitution? Does a U substitution work here? What? X squared. All right, let's try. U equals x squared. Then du would be 2x dx, or if you like, 1/2 du is x dx. So, see, previously the x, that worked as our u dv. Now it's playing a different role. It's part of our substitution, which is why, again, this comes back to the, don't jump in and say, aha, I'm going to take the derivative of x and the integral of e to the x squared. Because what is the derivative of e to the x squared? Correct. We don't have a good answer for that. You know? So, good. All right. Well, so what do we have? Well, if we carry this out, we'll have e to the u, since we're replacing the function x squared by u, and then the x dx is 1/2 du. So, in the interest of time, I'll just say that's 1/2 e to the u plus c. And is that our answer? We have to go back. This is an indefinite integral, so whatever you started with, here we started with x's, we have to end with x's. So 1/2 e to the x squared plus c. All right. Well, what about this last one? X cubed e to the x squared. What can we do here?
Hopeless.
Hopeless? No. No, 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 no. That's in the few pages. This is not hopeless. So remember, think, simplify. If nothing else, what can you do to help simplify this? And you might be like, well, how does one make things simpler? So I'll make a comment. Whenever you have functions inside of functions, you would not like that. So one thing is, can you somehow get rid of a function inside of a function? And how does one go about doing that?
Substitution. Y equals x squared.
Okay, we can do a substitution like y equals x squared. Sure, why not? Then we could say dy is 2x dx, or whoops, our dy. All right, it says 1/2 dy equals x dx. Now the problem is we don't have an x dx, we have an x cubed dx. Ah, we were so close. We were so close. I only had one more payment.
But can we just go with y?
Now, of course, we can, I should say, make a comment. The x dx, we can just pull an x off. If I pull an x off, what's left? X squared. So, does the substitution y equal x squared work here? It does. It becomes y e to the y, and then the x dx, we can put the 1/2 out in front. Okay, so we did substitution. So we say, aha, this is a substitution problem. Or is it just a substitution problem? Now what can we do? We can do it by parts. But we can be clever and say, hey, we did something like this already. So we can recycle. We know what the integral of x e to the x is. That's essentially the same thing, just replace x's with y's. So we say, so recycling this becomes 1/2 y e to the y minus 1/2 e to the y plus 1/2 c. Right? Just multiply everything by 1/2. Are we done? Got to get back. So everywhere we see a y, we put an x squared. So we get 1/2 x squared e to the x squared minus 1/2 e to the x squared. What about the 1/2 c? What can we do with that? C, where did the 1/2 go? It got absorbed. C is a constant, and constants are sponges. They can absorb other constants, and two constants can combine together and make one new constant. All right, so here's an example where, again, we might need to use a combination. So always be open to that possibility. All right, well, plenty of time, plenty of time. You might need to do integration by parts multiple times. And if you do, you have to be careful with the minus, because minuses, you have to keep track of them. So my advice, use parentheses as needed. Parentheses are your friends. And another piece of advice is be consistent in your choice for u and dv. Now, what does that mean? It'll be more clear once we start getting into it, but essentially, if you sort of change your mind and said, well, initially was the x part was the u and the dv part was the cosine or the sine, then at the next stage you say, I changed my mind. Now the x part's the dv and the cosine or the sine is the u. Well, what will happen is that you'll basically take one step forward and one step back, and you'll have made no progress at all. So once you commit, you're committed to see it all the way through. So be consistent. And there's this curious comment. In some cases, after several iterations, the original integral pops out. And that's not a bad thing. Because if it does, you can sometimes rearrange and solve. All right, so let's work through this problem here. All right, 2x squared sine of 2x. I'll go ahead and say it's an integration by parts problem. What do you want to have be the u? What do you want to have be the dv? So in other words, which part do you want to take a derivative of? Which part do you want to integrate? So which part do you want to take a derivative of? X squared. Because when you take derivative of x squared, things get simpler. Good choice. What are we going to take the integral of then? Answer is everything else. Once you've identified u, everything else is dv. So including the 2. So the 2 sine 2x dx, that's our dv. All right, so we'll make some notes here. U is x squared. dv is 2 sine 2x dx. What's the derivative of x squared? 2x. What's the antiderivative of 2 sine 2x? How about the antiderivative of sine? Negative cosine. Okay, so there's going to be a negative cosine 2x. Now, we don't need to worry about plus c's at this point. What goes in front of the cosine? I left a suspicious gap. You put 1. Why is it 1? Why is it not 2? Why is it not a half? Well, the answer is it's both. It's 2 halves. We still have a 2 from this 2. But when we integrate, we have to account for the 2 on the inside, so we have to divide by 2. So it's really 2 halves. So there's 1. All right, so according to integration by parts, this will become u times v. So we have x squared minus cosine 2x, and we evaluate 0 to pi. Because this is a definite integral, so we need to do our evaluation. Minus the integral 0 to pi, again, definite integral, of v du. So a minus cosine 2x times 2x dx. All right. Is it simpler? I would say yes. Here you had an x squared, and here you have an x. And a sine and a cosine are, for all intents and purposes, the same. All right. Well, let's do some evaluation really quickly. What happens when you plug in 0? You get 0 because of that x squared. What happens when you plug in pi? Well, you get cosine of 2 pi, which is 1. Then there's a negative 1, and then you get a pi squared. So this will become negative pi squared when you evaluate. On the other hand, we can combine these two minus signs together and to make it a plus. So we now have negative pi squared plus, thank goodness. We don't have to worry about the minus. That's a worrisome part. And we can write this in any order. So I'll write this as 2x cosine of 2x dx. All right. Well, we're still in integration by parts mode. What should be our u? What should be our dv? X should be what? Yeah. Remember what we said? Be consistent. So he said, hey, the polynomial part is our u. We've got to keep going in that direction. If we changed our mind right now and said, we're going to make this part be our dv, we would undo all our work. And that's no fun. We want to make progress, not go back. Okay, so x will be our u, and then we can still have our 2 cosine 2x be our dv. All right, so we'll make some notes here. U equals x, dv equals 2 cosine 2x. All right, now some computations. If u equals x, what is du? du is 1 dx, or just dx. What is v? What's the integral of 2 cosine of 2x? That's right. We saw the sign. And the 2's cancel. The 2 in front will cancel with the 2 that's going to come out and go downstairs. All right, so we still have that minus pi squared. We're not going to forget about it. Plus, now we have to do our uv. X sine 2x, evaluate 0 to pi. Minus the integral 0 to pi of v du, sine of 2x dx. All right. Well, we're near the end. We have our minus pi squared. When we plug in 0 into this middle expression, what do we get? 0. Because there's that 0 is 0 and sine of 0 is 0. When you plug in pi, pi times sine of 2 pi. Sine of 2 pi? 0. So this whole thing is gone. All right, well, what about the integral of sine of 2x? Well, we already did that. So we might as well just write it again. So the integral of sine 2x would be minus 1/2 cosine 2x, evaluate from 0 to pi. When you plug in 0, what comes out? You'll get a half. When you plug in pi, what comes out?
1/2.
A half. So what you get is minus pi squared plus a half minus a half, which becomes minus pi squared. Is it okay that we got a negative number? Actually, yes, it is okay, because sine can be negative. And in particular, sine of 2x will be negative from pi halves to pi. And if you think about what's happening, the 2x squared is biggest from pi halves to pi. So where it's negative, it's larger, so we should get a negative value out. All right, good. Any questions?
So we stopped doing it on the right side as soon as like all the outside x's were gone?
Well, we didn't need to do integration by parts in our last step. If that's why did we stop doing integration by parts, was there's no more need for integration by parts. I mean, our goal is to simplify to the point where we have something we can integrate. All right. Integral of e to the 2x cosine 3x. The classic kind of problem. Okay, what do you want to have be your u and what do you want to have be your dv? And before you say, there's basically not a wrong answer. So which one do you want to have be your u and which one do you want to have be your dv? You can phrase it as, which one would you rather integrate, or which one would you rather differentiate? Cosine 3x is what? Okay, so we want to differentiate the sines and cosines. So here's our u. And here, the rest of it is our dv. All right, so we'll make some notes here. So we have u is cosine 3x. we have our dv is e to the 2x dx. We need to find our various other pieces. What's the derivative of cosine 3x? Negative 3 sine of 3x dx. What's the antiderivative of e to the 2x? 1/2 e to the 2x, and the 1/2 coming from that 2 on the inside. All right, so by integration by parts, we now have the following. This is equal to u times v. So we have 1/2 e to the 2x cosine 3x minus the integral of v du. So we have our 1/2 e to the 2x and our minus 3 sine of 3x dx. We got lucky here with our signs, because a minus and a minus. So we'll clean that up just a little bit. 1/2 e to the 2x cosine 3x. I'll pull out the constants, plus 3/2 integral e to the 2x sine of 3x dx. All right, now we repeat our game. What's going to be our u? Yeah, we don't have a choice. We've got to be consistent. We chose our u to be the trig part. It's got to stay the trig part. And so then our dv is our e to the 2x dx. So we say, all right, great. Now make some notes. U equals sine of 3x. dv is e to the 2x dx. What's the derivative of sine 3x? 3 cosine 3x. The antiderivative of e to the 2x? 1/2 e to the 2x. All right. Well, good. So we have 1/2 e to the 2x cosine 3x plus, I'll have a 3/2 here, and then I'm going to put some brackets. We have uv. So 1/2 e to the 2x sine 3x. And then we have v du. We're going to subtract. So the integral of 1/2 e to the 2x 3 cosine 3x dx. All right. So we are at the following point. 1/2 e to the 2x cosine 3x. We'll distribute the 3/2 in. So 3/2 times 1/2 makes 3/4 e to the 2x sine 3x. Now I can pull a 3/2 out from the integral. And there's a 3/2 coming in, so that makes minus 9/4. Yes? Yeah, that sounds right. Integral e to the 2x cosine 3x dx. And now, we're like, cool, what's next?
We should just stop.
We should stop? No, we have a couple minutes left. We can figure it out before time expires. Well, notice this is probably a deja vu type of thing. It's like, wait a second, isn't that what we started with? And the answer is yes. Isn't that bad? The answer is maybe. It would be bad if you had a 1 in front. But we don't have a 1 in front. So what can we do? What we can do is we can move it to the other side. Now, I have to pause and ask a question. Does this equal that? And why is the answer no? No, don't worry about the 9/4. Does this integral equal that integral? And why is the answer no? There's a plus c. There's a subtle plus c that floats around. So if we move this across, so this is a minus 9/4, add 9/4, you'll get 13/4 integral e to the 2x cosine 3x dx is the 1/2 e to the 2x cosine 3x plus 3/4 e to the 2x sine 3x. But remember, these actually differ by a plus c, so don't forget to put it in. It's very easy to forget it on these integrals. Is this our answer, and why not? We didn't want 13/4 times it, right? We want this, not that. So multiply both sides through by 4 over 13, and we get the integral of e to the 2x cosine 3x dx. Well, so 1/2 times 4 over 13 gives you 2 over 13 e to the 2x cosine 3x. And then 3 over 4 times 4 over 13 gives you a 3 over 13 e to the 2x sine 3x, and then a plus c. And that is our answer.